In this video, we want to apply our understanding of two-way tables to diagnostic tests and to begin the conversation of analyzing the test and determining some key features that we'll refer to later in this module. So first, let's just interpret what we have. We're looking at a two-way table where we are comparing and looking at people who have gone in to the doctors or lab to get some sort of test or screening. Some of them have the disease. They don't know that. That's why they're going to get the test. But there are individuals who come in to take the test that have the disease and those that do not have the disease. Now, depending on the test, some of those individuals will test positive and some of them will test negative. Now, just interpreting this table, what we see, there are 15 total people who came in who had the disease. There are then 635 people who do not. So that's just, again, looking at the table, across the rows, and interpreting what we have. The total number of people who tested positive, if we look at those in this first column here, are 70. There are 70 people out of the 650 people who tested positive, and there are 580 people who had a negative result. So clearly, some people who've come in have the disease or do not, test positive or do not. Some of them are going to have a result that matches their condition and others that don't. And so if we just look and interpret that, those who have the disease, we would expect them to test positive. That would be a true positive result. That's what we call a true positive. And the reason it's a true positive is because it is true that the person has the disease and they had a positive result. So that is good for the test to be able to identify that with the individual. Those who come in without the disease, who test negative, there are 573 of those individuals, and that's called a true negative. That's the result that we would expect. Now, again, what we can also determine is the tests that are not accurate in terms of not matching whether or not the person has the disease. So those, what we would call false positives and false negatives. So first, if we look at the people who have the disease, who come in and test negative, there are 7 of those individuals, that's called a false negative. These are the individuals who have a false negative result. And then we have those who come in who do not have the disease and test positive, and that's a false positive. So this is just the number of individuals who have that particular result. Now, clearly, we want the test to be able to identify true positives and true negatives. And if that's the case, then the test is doing its job, the diagnostic test. We use the phrase sensitivity to describe one of these things. So sensitivity refers to the test's ability or the strength of the test to be able to identify those who have the disease. So the sensitivity refers to, if somebody comes in and has the disease, what is the probability that they're going to test positive? That's referred to as the sensitivity. And we refer to this as it's a conditional probability. So this is the probability that somebody has a positive result given that they have the disease. So out of all of those who have the disease, how many of them are going to test positive? Now we know as a fraction, this is going to be the total with the disease. Oops. Total with the disease. And up top, we have a positive result and they have the disease. So what we see in this situation is that there are 15 total people who have the disease. And out of those 15 people, 8 of them tested positive. So we get an 8 out of 15. Now, you could convert that into a percentage. You could convert that into a probability. And let's actually convert this into a percentage. Putting this in the calculator, we get this is approximately 53.3%. So this test has a sensitivity of 53.3%. Again, the sensitivity is identifying the percent of individuals that have a disease that come in and test positive. And we would want this to be, and we would hope that a test would have a high sensitivity, meaning that if somebody has the disease, there's a high likelihood that they'll test positive on the test. Otherwise, we don't want a lot of false negatives. That's not a good thing. What we want to look at next is called the specificity, and that is referred to, let me just write that out, specificity. And with the specificity, we're going to look at those that have a true negative. In other words, what's the probability of the test identifying someone with a negative test result if they actually are negative, so they don't have the disease? So what is the probability that the test will be able to correctly identify those without the disease? And so we want to look at the true negatives, so those that are negative and not have the disease. So that's referred to as the true negatives. Just write that out. And we want to divide that by the total without the disease. So this is the true negatives out of all of those who do not have the disease. What we see is that we get a total of 573 people had true negatives, and that was out of the 635 who we know came in, and we won't always know, but we know in this case that they don't have the disease. So out of the 635 people, 573 of them do not or tested negative with a true negative. So when we put this into the calculator, we should get that this percent is about 90.2% if we round to the 10th place. So the specificity as a probability, if we leave it in fraction form, is 573 out of 635. In a percent form, we get 90.2%. We also want to be able to calculate what's known as the false positive rate or percent and the false negative rate or percent. And this is the rate or the percent. You could also calculate it as a probability, which we see that somebody coming in with the disease tests negative, or somebody coming in without the disease tests positive. So, respectively, the false positive are those that come in without the disease who incorrectly test positive. The test identifies them incorrectly as positive. And those coming in without the disease, the test incorrectly identifying them with a negative test result, that's called a false negative. And so I have these rates written out in the conditional probability form. So with the false positive, we want to essentially calculate the probability that somebody has a positive test result, given that they do not have the disease. So in this particular situation, what we want to think about is, well, how many people come in without the disease? And out of those individuals, how many of them test positive? It's almost the complement, if you will, of the sensitivity, or excuse me, the specificity, because the specificity correctly identifies those without the disease, but the false positive incorrectly identifies those without the disease. So when we consider all of those who do not have the disease, there are 635 people who do not have the disease. That's kind of the given, right? We take the given and we write that as our denominator. And out of those individuals, the number of people who had a positive result were 62. So this is 62 out of 635. So if we were to convert this into a decimal and a percent, up to you how you want to do this. As a percent, or excuse me, as a decimal, you would get about 0.0976, which is about 7.8 8%. So all of these are approximate here. I rounded to 4 decimal places for the decimal, converted that to a percent, round to the nearest tenths place there. But all of these, fraction form, decimal form, percent form, hopefully you should be comfortable going between all of them. Next, we want to calculate the false negative rate. So people coming in with a disease, unfortunately, some of them will be incorrectly identified with the test, with a negative test result. So let's think about, well, how many people coming into this facility have the disease? It looks like there are 15. And out of those 15 individuals, unfortunately, 7 of them are going to have an incorrect test result that doesn't align with their status. So 7 out of 15, if we were to calculate that as a decimal, we get 0.46 repeating. So we round to the hundreds place or thousands place. The other one I rounded, this one, we have a decimal that goes on forever, so we'll just write it as a 0.46, which as a percent is about 46.7%. Fraction form, decimal, percent. What this tells us is that for someone coming in, if they have the disease, there is a 46.7% chance that they have a negative result. This is referred to as the false negative. The last thing that I want to mention, which is not on here, and I'll make a little space for it if I zoom out, we want to talk about the accuracy. The accuracy of the test refers to the test's ability to correctly locate those who either have the disease or do not. And so when I look up at the chart, there are 2 places where we have true positives and true negatives, right? Those existed here. 8 of these individuals, that was a true result, and 573, that was a true result as well. So the accuracy is simply the correct results, and I'm going to put this in quotes, and then I'll write it out in a different way. But it's the correct results, those with the correct results, out of the total number of people. So in this particular case, and writing it in a different way, we have the true positives plus, and I'm going to put that in quotes so it's a little clearer, plus the true negatives. And we're going to divide that by n, which is just the total number of people. In this problem, if I write that up here, we had 8 people who had a true positive, 573 who had a true negative, and there were 650 people that had this test. So again, I'm just going to write up a little bit backwards here, but when I add those together, I get 581 divided by 650. I could leave that as a fraction. If I wanted to write that as a percent and a decimal, 581 divided by 650. As a decimal, this is approximately 0.8938, which means this is about an 89.4%. All of these are approximately, depending on how we are asked to represent this information in fraction, decimal, or percent form. We see that the accuracy of this test is 89.4%.